Welcome to Pre-Calculus. Today we will find dimensions of triangles using angles of elevation. We'll take a look at 4 examples. Our first example is this scenario. Tina flies a kite with a 100-foot string. The angle of elevation of the string is 52 degrees. How high off the ground is the kite? I always start drawing a diagram with a word question like this one. So here is the ground. And we'll imagine that Tina is standing here on the ground, flying a kite up in the sky. And what we know are 2 measurements. The length of the kite string is 100 feet. And if I consider this as a right triangle, I also know this angle here between the kite string and the ground is 52 degrees. And our task is to find how high off the ground is the kite. So I'm going to label that with the dimension y. So again, this side of the right triangle, this y, it's not really an object. It's really just a height. So to set this one up, we really need to think which trigonometric ratio would involve these side lengths 100 feet and the one I'm looking for, y. So in terms of how they are positioned in reference to this angle 52 degrees, my angle of elevation there, this y is going to be opposite the angle of elevation, and the 100 feet, since it's opposite of what we're considering the 90 degrees in this right triangle, is my hypotenuse. And that allows me to set up a trigonometric ratio that involves the opposite side and the hypotenuse, and that's going to be sine. Remember, we defined sine of theta to be opposite divided by hypotenuse. So what we'll do for our question is we're going to say that the sine of specifically 52 degrees is going to be equal to y. That's what I'm looking for. That's the opposite measure divided by 100. And that gives me an equation whose solution is going to give me the height of that kite. Solution's pretty straightforward here. All I've got to do is multiply by the 100 to cancel it. It'll do so there on the left, or on the right side. On the left, it's going to show up as a multiplier. And that expression, 100 times sine of 52, is going to give me the height of that kite. We'll jump over to the calculator to get a number there. 100 times sine of 52. And recall on Desmos, our sine functions here under the functions tab, it's the very first trigonometric function. So 100 times sine of 52. I do need to make sure that the calculator is set to degrees. So I'm here in the settings there with the wrench, and it is on degrees. So we're good. And it looks like this measurement's given to us as 78.8. We'll head back to our notes to finalize that answer, 78.8. So with this example, we were looking for a height. My units here are going to be feet, 78.8 feet. And that's how high the kite is off the ground. Our second example is really looking for an angle. So here, this one is saying if a 73.0 foot flagpole casts a shadow 51.0 feet long, we want to know what's the angle of elevation of the sun to the nearest tenth of a degree. So a diagram is very helpful in this case as well. So like in the previous one, I'll set the ground first and a flagpole waving in the breeze. And what we're imagining is, in fact, let's have it wave the other direction so it doesn't mess up our shadow. We're imagining that the sun is there in the sky and that it's casting a shadow from the flagpole onto the ground. So the dimensions that I know are the height of the flagpole at 73.0 feet. I also know that this distance of the shadow, so this is not to scale, but it gives us an idea about the setup, is 51.0 feet. And what we're looking for is the angle of elevation theta. So just like in my previous question, I want to use those pieces to set up a trigonometric ratio that involves the opposite. So that 73 feet is opposite of the angle theta, and the adjacent leg. Notice hypotenuse is really not part of this scenario. So the one that I'm looking for, there's a couple trig ratios that involve opposite and adjacent. It could be tangent, it could be cotangent, but tangent is going to be defined as opposite divided by adjacent. So we'll go with tangent. We could have used cotangent. Remember, cotangent's adjacent divided by opposite. Either one will work. Once I've got that selected, I'm going to set up my equation. Tangent of theta. So notice I'm just putting it generate because that's actually what I'm trying to solve for, equals 73.0 feet divided by 51.0 feet. Once I have that equation set up, I can clearly see to solve this, I need to apply inverse tangent to both sides. And on the left, inverse tangent is going to cancel tangent, and we're just left with theta. So theta is equal to the inverse tangent of 73 divided by 51. And we just need to calculate that. So again, we'll go to the calculator. Inverse tangent of 73 divided by 51. On Desmos, the inverse tangent's also under the functions tab in this middle column. Those are my inverse ones. Select it and then type in my ratio 73 divided by 51. And that gives me 55.0607 degrees. We'll round to 55.06. Heading back to the note screen to finalize that answer, 55. In fact, I see our units here to rounded to the 10th, so we'll go 55.1 degrees. So with those two examples, really we were just looking at one right triangle that involved our angle of elevation. We'll take a look at an example that involves multiple right triangles that are stacked within each other. Here I've got a person standing at a point some distance away from the base of an antenna tower, measures the angle of elevation to the top of the antenna as 47 degrees. We'll start with that first part. So this has multiple parts. So I've got an antenna tower that's sending out a signal. And I know that there's a person that is standing some distance away from it. I don't know that distance. I'm going to call that X. What I do know is that the angle of elevation for that person is 47 degrees. So that's that first sentence. Now, second sentence begins, a second person standing 33.0 feet farther from the antenna than the first person measures the angle of elevation to the top of the antenna to be 42 degrees. So another person is standing a bit farther from the antenna, in fact, exactly 33.0 feet. And the angle of elevation from that person, since that person's a bit farther, it's a smaller angle, 42 degrees. And what we're trying to solve for is how far is the first person from the base of the antenna tower? I'm looking for that X. Now I need to involve a third measurement here, which is the height of the tower. I'm not going to use it, but to help me really create and solve a system of equations. So I'm going to put that y there, but again, it's something that I won't solve for directly. It's going to help me with the setup. So I want to start with this first person's right triangle. So if I consider that 47 and this y, that's opposite. And the x that I'm looking for is adjacent. And I do that again to help me think how to select a trigonometric identity. So like our previous example, that's tangent. So my first equation is going to be the tangent of 47 degrees is equal to the opposite y over adjacent x. Now, I want to solve for y. In fact, what I need to do is distinguish that kind of as a piece there that stands out. I want to solve for y. So I'm going to multiply by x to cancel the x's. And it gives me an expression here that from one point of view, y equals x times tangent of 47 degrees. I'm going to hold on to that. What I want to do is I want to set up a second right triangle with the second person, the one in red here. So for that person, it's also tangent, but the angle is 42 degrees. Still y is the opposite side, but the adjacent side's not just x, it's x and 33 more feet. So I'm going to call that x plus 33. Just like we did on previous example, I'm going to let y stand out there. I want to solve for y. So to do so, I'm going to multiply both sides by x plus 33 to cancel there on the right side. And what I want to do is distribute tangent through x plus 33. So what I've got here for this second version is that x times tangent of 42 degrees plus 33 times tangent of 42 degrees also equals y. So now what I'm looking at are these two equations. Let me highlight them. And what I need to notice is that they're both solved for y. Now, if they both equal y, that means that the left sides also equal each other. So it's a strategy we have from systems of equations from algebra. Since the right sides are the same, I can set the left sides equal to one another. And that's good news for us because that gets rid of variable y and allows us to solve for x. So now what we got is x times tangent of 47 degrees equals x times tangent 42 degrees plus 33 times tangent of 42 degrees. At this point, I want to move my two terms that have x in them to the same side. So I'm going to subtract x tangent of 42 so that it shows up here on the right side. It cancels on the right side and it shows up on the left. So at this point, what we've got is x tangent of 47 minus x tangent of 42 equals 33 tangent of 42. And what I need to do now is, I got my eye on the x. Because it's in both of those terms, I can factor it out. So what we've got now is x times the tangent of 47 degrees minus tangent of 42 degrees equals 33 times tangent of 42 degrees. And our solution's right in view. All we've got to do at this point is divide by everything but x. So I'm going to divide by tangent of 47 degrees minus tangent of 42 degrees. That'll cancel. And my value for my distance here is going to be given by this fraction on the right. I'm dividing there also by tangent of 47 degrees minus tangent of 42 degrees. And that I want to take to the calculator, get an answer, and finalize here. Let's take it over to Desmos. So our setup here is fractional. It's 33 times tangent of 42 degrees over tangent of 47 degrees minus tangent of 42 degrees. And that's giving us right away 172.79 feet. We'll take it back to the note screen to finalize. Again, we had solved for x there. X equals 172, and we'll round to the nearest tenth, 0.8 feet. Our last example also involves two right triangles. Here we've got two students that decide to estimate the height of a flagpole outside their school. So again, I've got a flagpole. One student positions himself due north of the pole. So we'll put the direction north to the upper right. So there's that first student standing exactly north of the flagpole. While the second student positions herself due east of the pole. So east is going to be 90 degrees from the north. So we'll place our second student right there. Now, if the two students are the same distance from the pole, so these lengths between each student and the pole are the same, so those are congruent, and the two students stand 25 feet from one another, so this is 25 feet here. We want to find the height of the pole if they both measure their angle of elevation from the ground to the top of the bolt to be 56 degrees from each position. So lots of right triangles here. Essentially, this angle is 56 degrees. There's another angle here, but I don't want to add that because it's really going to crowd out my diagram. So I got to keep in mind that this triangle that we drew at first, if I just highlight this one, that's on the ground. Whereas this triangle on the upper side of the diagram, that's actually perpendicular to the ground. It's like a vertical, invisible wall. Now, I got to keep in mind what I'm trying to solve. I'm trying to solve for the height of the flagpole, which we'll just label Y there. So I'm going to notice something first, that this triangle that's on the ground, the one highlighted in blue, is a right triangle because these students are standing due north and due east. And north and east are 90 degrees from one another. Because these sides are perpendicular, they're perpendicular, but they're also congruent. I was told that that's the same distance from each student to the base of the pole. This is a 45, 45, 90 special right triangle. So if I think about how to get from 25 feet over to this horizontal distance between the first student and the pole, that's going from the hypotenuse to the leg. So again, if I think about my 45, 45, 90, that was x times the square root of 2. Well, the piece we've got is this x squared root of 2. So to get over to the leg, I just need to divide 25 by the square root of 2. So we'll do that first. Remember, I can't divide by an irrational number, so I need to rationalize the denominator. And so this length here, and we'll put it in red because it's matching that upper triangle, is going to be 25 square root of 2 divided by 2. I'll put that measurement here. So again, this is the, in a way, a vertical invisible wall triangle now. So now I'm on this upper triangle, and I'm really ready to set up a trig ratio. So if this 56 is the angle of elevation, this y is going to be opposite of it. And the piece we just calculated, 25 square root of 2 over 2, is adjacent. So I got to think the trig ratio that it involves opposite and adjacent, we just used it, is tangent. So my setup for this problem in terms of an equation is going to be the tangent of 56 degrees equals y, opposite, divided by adjacent, 25 square root of 2 over 2. Once I have that set up, solution is very simple to find y. I just need to multiply by 25 square root of 2 over 2 to cancel here on the right. That'll cancel. And then multiply tangent 56 by that same 25 square root of 2 over 2. And all I got to do again is, once I've got that expression solved for, I just need to calculate it on the calculator. So we'll type it in, that fraction first, 25 times the square root of 2 over 2 times tangent of 56 degrees is giving us a height of about 26.21 feet, 26.21 feet. So we'll head back to our notes just to finalize the example. In this case, y equals 26, we'll round to 2.2 feet. Thank you for joining for these 5 examples of using trigonometric ratios to solve questions that involve angles of elevation. Thank you for joining. See you soon.